Good evening, everybody. Welcome to our NSS Space Forum this evening, How Science Keeps Earth Safe from Hazardous Asteroids. So on behalf of Larry Ahern, Vice President of Chapters, my name is Bert Dicht. I'm the Managing Director of Membership, and I welcome you. We're glad to have you back. It's been a while since we've done a Space Forum. I think our last Space Forum was back in April. We took a little bit of time off for the ISDC and some other things we had to do. So we're going to be getting back on track to a regular schedule. So we're glad you're back. Hope you've had a good time, and we're just about to start the summer. So here in the US, so things are looking good for us. So thank you all again for joining us. As always, I'd like to go through a little bit in terms of the agenda. We'll do a very quick, brief intro to our virtual etiquette. Some NSS announcements will follow. Then I'll talk about what's coming up. We've got a number of space forums scheduled, including one town hall, and then we'll get right into the program, and then we'll close out for the evening. So virtual etiquette-wise, if you'd like to submit a question, we always encourage you to use the Q&A function because that's seen by the panelists directly. There's not other comments, no other comments. It's easy to pick out the question and answer the question that way. But you are absolutely welcome to submit something through the chat. I ask that you be respectful of the panelists and audience because in most cases, everyone can see the chat. We will give you the opportunity to ask a question over the microphone if you so desire. So we'll see how much time we have for that. One thing I want to call your attention to, you probably all know I'm a big Snoopy fan, and you see the Astro Beagle Snoopy there was serving as the zero-G detector for the Artemis 1 launch. Well, I just saw big news that he is now in California at the Charles Schulz Museum in Santa Rosa. So you see a picture there. Looks like he's floating, but I believe he's being held there. So I just thought I'd share that. So it's interesting. He went all the way around the moon, and now he's taking his time and relaxing and retiring in California. So I just thought I would share that as a great thing related to the space program. As always, we encourage you to give to our cause. If you're enjoying these programs like the Space Forums and Town Halls, please donate to support the National Space Society. I want to give a shout out to all the members and donors who have supported our most recent fundraising activity, and we really appreciate your support and your generosity. I will post this link into the chat so that you can use that, and we feel free, if you have any questions about donations, to let us know. But I'm going to thank everybody in advance for making the donation. Also, please complete the post-Space Forum survey. It only takes a few minutes to complete it. The survey is anonymous, and your feedback really, really helps us in making decisions about where to go, how to improve these space forums. And we really appreciate all the comments you provide. I just want to give a shout out to our finished up ISDC 2023. It was a great success. More than 1,000 people, including about 300 plus students, attended. And that was in Frisco, Texas. So you see a few samples of some of the photographs. We had great sessions. You can see we had Jared Isaacman, Bonnie Dunbar, Eileen Collins. As I said, there were plenty of students there to enjoy, and they did an amazing job with their poster contest. So I encourage you, the next ISDC is going to be in Los Angeles. So we'll be sharing more about that in the coming months, but hopefully we'll be able to see you there as well. Also, the latest issue of Ad Astra magazine has now been published, and it is in the mail. This is the 2023 quarter 2, volume 35 issue, and it's a issue dedicated specifically to space education. There is just a sampling of some of the great articles in this issue. So look for it. I know mine has not yet come in the mail, It usually takes anywhere from about a week to about 3 weeks because of the way the mail system works with how we ship it out. So look for it over the next week or so, and it's a great issue, so I encourage you to read it. As always, a shout out to our editor-in-chief, Rod Pyle, for, again, an amazing job, and all the contributors. Also, I would like to call your attention to the NSS blog. This is kind of a resource a lot of our members don't know about. So you can sign up for this, so you'll get a notice when a new blog is posted. You can always just go to the website itself, but I encourage you to sign up because you'll get a notice when anything new is posted. We do announcements about what's happening in NSS, book reviews, policy issues are discussed, and press releases, and a lot of other things. So I really encourage you to take a look at that. I think you'll enjoy many of the postings. And if you have something you might want to post, there's also information about how you can make a post as well. So, because we'd love to hear from you. So with that and our introduction on everything related to NSS, I guess I'll call that our commercial announcements. Let me just share what's coming up in terms of our space forums and town halls. We're not going to do another one until July 13th. The normal 2-week cycle would put us into July 4th week here in the United States, and we just decided it might be better to skip that week. But we have Dr. Doug Plata, who's going to be talking about the Space Bear and Instabase. Really interesting discussion. On the 20th, the anniversary of Apollo 11, we're actually going to be doing an NSS leadership town hall. So you have a chance to ask questions of the NSS leadership. We'll have some prepared discussion presentations, so please join us for that. The one that is tentative right now is for July 27th, the Astronaut Scholars Panel. This is from the Astronaut Scholarship Foundation. It's tentative. My guess is we're going to move it later because we're trying to get about 4 to 5 or 6 scholars to present that evening, and it's tough to get everyone on one night. So that one might change. We'll know better on the 13th about that. August 3rd, we're doing a joint space forum with the Huntsville, Alabama Al5 Society, and that's on the Parker Solar Probe with Dr. Nicole Fox from NASA. And then on August 10th, 3D printed habitats on the moon with Melody Yashar. Melody did an amazing presentation at the ISDC on these 3D printed habitats. She's an architect and really, really fascinating. And then we have a whole lot of things we're working on to get in September and October. Some of those I've shared in the past. So look for more information at the next Space Forum. So now I want to actually get to our program for this evening. And as we talked about, it's how science keeps Earth safe from hazardous asteroids. And our guest speaker tonight is Jonathan Dagle. And Jonathan is the chair of our NSS Policy Committee and also our Planetary Defense Policy Manager. He's a technologist, he's a futurist, he's a strategist, he's a retired Air Force officer. What he does now is he helps organizations craft strategies and implement technologies to better achieve their goals. And he's going to be talking tonight about planetary defense. And we're glad to have Jonathan. So Jonathan, it is my pleasure to turn this over to you. I'm going to stop sharing. There we go.
Thank you, Bert. That's great. Thanks. Appreciate the introduction. I'm going to put out a plug for a book that I love, which I don't, because I will forget later, but it's been instrumental to my understanding of asteroids and so forth. And that is the great near Earth. You can tell that I am an asteroid geek because I'm going to recommend this book, Near Earth Objects, Finding Them Before They Find Us, by Donald Yeomans. I don't know if you can see it because of the Zoom is going to try to see it. It's a great, fantastic book available from Amazon or even your local bookseller. Which is where I got mine. In the topic of this presentation, I sort of highlighted all the science for keeping us safe. So I really found that there's not enough time to talk about all of this. So I am going to tell you a little bit about asteroids themselves, perhaps that you did not know. Maybe all of you know this, but anyway, so we'll see how this goes, and then I will try to answer as many questions as I can at the end. I'm very happy to talk about asteroids or space policy or anything else that you are so inclined to discuss. So let me share over here to my video. Voila. Right. So Bert has already told you a little bit about me, right? So that's the same thing. But if you want to get in touch with me, it's in the show. So reach out. So here's what we're going to talk about a little bit about the threat, about, what are asteroids. We're going to actually talk a lot about asteroids, which maybe too much. We're going to briefly talk about planetary defense and how it works. And then, what we're doing now, what we're going to do in the future regarding planetary defense. And then we'll end and I'll ask you or answer the question, what can you do to help support planetary defense? So this is the threat. I think many people are aware the asteroids have been hitting the Earth for basically as long as the Earth has existed. I'm just going to look at some more relevant recent impacts here. Of course, the 66 million year ago Chicxulub extinction event, generally accepted to be caused by a about 9 or 10 mile wide asteroid that struck near the Yucatan Peninsula. Gigantic, very, very large asteroid created perhaps a 90-mile wide crater and resulted in the extinction of the majority of all living animals at the time, including the non-avian dinosaurs, which, end of Jurassic Park, Jurassic World. So every time I see the birds in my lawn, I think that they're the dinosaur survivors because they are related. Somewhat more recently, 50,000 years ago, meteor crater. So I don't have an image of the extinction of the dinosaurs. There is a good show on PBS that covers that, talks about what happened when the asteroid impact occurred, what happened in a place that's now in central United States. But there's a great, fascinating fossil record there telling the story. Meteor crater is a crater that we can go and visit. I don't know if any of you have ever been there. I've been there. It's pretty impressive. And this was a relatively modest asteroid, 160 meters, or I'm sorry, 160 feet, which is much smaller than our metric for the potentially hazardous asteroids that we look for today. That created a 3/4 mile across crater that is more than 500 feet deep, and it's still very well preserved. There's a very interesting history of this asteroid, that it's, the crater rather, that the crater, which is often called Barringer crater. I think there's some unhappiness about that because of the ownership of the land. In any event, Barringer, a geologist, bought this thinking that he was going to mine the asteroid resources that were buried at the center. Turns out there weren't any because they were all vaporized essentially and spread out all over the area. Anyway, so this crater is very well preserved. It's thought to have resulted, the impact, I should say, the impact was almost certainly a very metallic object. And so there are metal deposits out there, probably an iron meteorite, which is the reason for the outsized crater for an asteroid of that size. It's thought to have caused a fireball that would have expanded to 12 miles, killed the wounded animals within 15 miles, and caused basically a blast pressure shock wave up to 25 miles away. So quite a bad situation if something like that were to happen in any sort of remotely populated area today. More recently than that, in the not prehistoric past, 125 years ago in 1908, the Tunguska event in Siberia. This is generally thought to be a comet or comet fragment that exploded in the air as an airburst, and thus there was no crater. Still, when investigators got to the region from Moscow, it took them several months to get there, but still they could not figure out where the crater was. They thought there would be some sort of a crater, but they couldn't find one. And what they did find was just an area that was completely devastated over 5 square miles. And then the amazing thing was hundreds of square miles of forests that had just been leveled. And so this is how they have come to the conclusion, they've approximated the size of the airburst. I've read some reports about the eyewitness accounts of people several hundred miles away who were knocked off their feet. One Siberian man said that he had been standing on a porch, and this sudden thunderous sound and the vibration, and he fell off, he was knocked off his feet, windows were broken, etc. So they think that this airburst was perhaps 10 to 20 megatons in yield, which is I'm here to tell you very, very large. I mean, that's larger than the largest, well, it's larger than the very largest nuclear weapons that were kept in the Soviet inventory. I don't think we really kept weapons that large, but it was pretty big. And as an airburst, I mean, there was not any crater to speak of, so nobody can really have pictures of the crater. The event that we all saw on dash cams from 2013, just 10 years ago in Chelyabinsk, that was thought to be only about a 65-foot wide asteroid, exploded at 95,000 feet, which is quite high. This is 3 times higher. Well, it's two to 3 times higher than an airliner would be flying, caused damage to buildings, broke windows, collapsed some structures, and injured some 1,600 people. That was thought to be an estimated yield of 400 to 500 megatons. So you're thinking that's about 20 times, at least 20 times the size of the Hiroshima atomic bomb. So these things are dangerous, and if the words aren't enough, this is a graph, or a map rather, from the Earth Impact Database, which is maintained by a university in Canada, but it lists all the scientifically confirmed impact structures. So they're not necessarily craters, but they're things that demonstrate that some sort of impact occurred, because the Earth likes to weather away the craters, so they're very hard to see. And through geological processes, they tend to disappear, even though some still exist and you can find them. So every circle on here is one of the 190 known impact structures, and the size of the structure indicates how large it was. So this key, when I looked at this map the first time, I was sort of thrown off. I was like, oh, there was an asteroid that hit Antarctica. No, that's the circle that shows you how large a 100-kilometer asteroid crater would be. So down here on the left, you see the size, the relative size of the impact crater, and the color indicates how many million years ago it was. So a red one is less than 1 million years ago, brown, green, et cetera, et cetera. Anyway, so the point is, here you see Chicxulub, and that's green. So that was 66 million years ago, and that equates to 10 to 100 million years ago on this graph. So that's a significant one. Let's see, meteor crater is probably in here somewhere. it looks like it's this tiny dot. There's a tiny dot in Arizona, not that big. I guess they figure it's not quite. It's almost a kilometer across, so it doesn't get a lot of credit. Of note, so there's a crater. If I click this, it's not gonna work right. But there's a crater in Sweden that I was not really aware of before, but it is thought to be about 350 million years old. It's the blue one it's a very large blue one that seems to be in Sweden. I don't think you can see my cursor. But that crater may have a correlation to the large extinction event that occurred before the dinosaurs, what's known as the Great Dying. It was such a large extinction event. I mean, so much more impactful than even the Chicxulub event, that more species died off, and it was, very it was quite interesting if you're a paleontologist, I guess. It's not really my area of expertise. So so this is evidence that these asteroids have been leaving their mark for a long time. But not just the ones that leave their mark. This is just a graph of all the known fireballs that were reported by certain US government sensors from 1988 until just this year. Quite a lot. The graph shows the size, the relative magnitude. So the closer it is to red, the bigger it is. You can see there's one red one here in Siberia, which is the aforementioned airburst in Chelyabinsk. So these things are going off all the time in the air. These would be the smaller asteroids, which are probably let's say 50, 60 meters or less. And some of them are quite small. I mean, I saw a report recently, in the clickbait news about, some terrible asteroid the size of a minivan, is going to come close to the Earth. And there are many asteroids of that size, but they're largely inconsequential because it has to be of a certain size before it can cause a damage like we saw in the Siberia, or in Russia, in Chelyabinsk. So anyway, so let's get on to the asteroids themselves. What exactly are these things? Well, the asteroids are interesting scientifically because they are the oldest bodies among the old. I mean, everything in the solar system arguably is old. They're some of the oldest bodies that have not had any weathering or substantial changes. They've been very much stagnant for a very long time. Perhaps they have elements that date to 4.6 billion years ago when the solar system formed, and they are sort of the primordial remnants of that time. Of course, many of them have collided with one another, creating both smaller asteroids and larger asteroids. When some of these things collide, they well, we'll get to the composition later, but some of them come apart because they're really not held together very well at all. They're just held together by a weak gravitational force that's keeping the dust and particles, small rock-like elements, together. And so when they collide, they can break up into smaller pieces, or they can break up and then reform into one larger asteroid. So I thought that there was the question, how many asteroids are there? Well, there are just under 1.3 million asteroids cataloged by the Minor Planet Center. That includes all types of asteroids throughout the solar system that have been cataloged. So not just near-Earth objects, that near-Earth objects are substantially less. If you added up all the mass that was of the asteroids throughout the solar system, it would still be somewhat less than the mass of our moon. I think a fair amount less, not like half, but somewhere, let's say, between half and 100%. Let's not put too much detail on that. The interesting thing about asteroids is So, everyone knows about the asteroid belt, and that asteroids are all largely orbiting the sun, just like the planets. It's just they have rather more exotic orbits than the planets, and there are a lot more of them than there are the planets. Jupiter plays a very profound role in what is going on with asteroids. So if you look at a map of where you see asteroids in the solar system, the primary place is in what I grew up learning about the asteroid belt out beyond Mars before Jupiter. And I mean, that's what's referred to as the main belt. That is where the vast majority of asteroids are. It's quite a thick, large, torus-like area that has many asteroids. And they are there mainly because of the gravity of Jupiter that has swept them, that sweeps through that area and pushes them. So they get tugged by Jupiter and they get tugged by the sun. And so they would basically just sort of have collected there as sort of a solar system gutter to collect the remnants that are circulating around. So that's not the only asteroids, though. We also see the somewhat less well-known, but still well-known Trojan asteroids and the Greek asteroids. Now, interestingly, they're all sort of referred to as the Trojan asteroids, but the Greek asteroids precede Jupiter and the Trojans follow Jupiter in its orbit as Jupiter goes around the sun. And then there are also the Hildas, which are spaced out at sort of 3 positions around the sun, and they all stay largely in sync with Jupiter. Now, it's not too hard. Some of you might be thinking, well, gosh, isn't that those Greeks, they look like maybe they're at L4, and the Trojans, they look like maybe they're at L5, and the Hildas, at least some of them, look like maybe they're out at L3. And that's exactly what's going on. I mean, in a sense, because those are gravitationally stable places where these things tend to collect. So anyway, so that's another source of asteroids, a lot of them around Jupiter, also around Saturn. I don't know, this may surprise some of you, but there were recently discovered and confirmed some Trojans. There are even Trojan asteroids around Earth, so that follow Earth in its orbit behind, somewhat ahead. In fact, this, I'll just go back, this illustration, so it's not, there really are not a lot of good pictures of asteroids because they're very dark, they're very far away, there've only been a couple missions going there. So most of the pictures, they just look like, a white streak or something. But so they have a lot of illustrations. This illustration on the bottom is a Trojan asteroid that was identified in 2005 by the oh heavens, by a telescope, I think the Lowell Observatory in Arizona. So interesting point of reference. So in addition to these Jupiter area Trojans and the Saturn ones as well, and the main belt, you have of course, the near Earth objects, which are sort of represented by these green and red dots in this graphic. I'm not really sure why they're green and red, but that's what they're inside the main belt. Now, the Kuiper belt is an interesting thing. You probably have heard of the Kuiper belt. It's an area of mostly icy and dusty bodies, which are out past, basically starting at Neptune's orbit and going further. Pluto is actually considered to be in the Kuiper belt. I have just pull up. I can't see my notes here. The interesting thing here about the okay, so if you're looking at this image on your computer, that's probably about 10 inches across, roughly. So if that's the case, and Jupiter is 5 astronomical units away from the sun, then Neptune, which is 30 astronomical units away, is about 28 inches out to the left or right or wherever from where the sun is on your computer. That's where the Kuiper belt starts. And that continues out another, well, to 56 inches, so about 4.5 feet away from your computer. And then well beyond that is the Oort cloud. The Oort cloud is way, way far away. And so I don't really know where I imagine it's like in the, it's not your neighbor's house, it's several houses away. But those are the places that the short period comets and long period comets, short period meaning generally less than 200 years in orbit to orbit the sun. The Oort cloud is where the longer period comets come from. I guess the thing I didn't mention that I alluded to before was that the role Jupiter plays in this. So not only does Jupiter bunch up a bunch of these asteroids in its orbit and sort of maintain the asteroids in the main belt orbit, but Jupiter is the primary agent that kicks asteroids out of the main belt and sends them into the solar system. So into the inner solar system. So those asteroids, as they get perturbed, if they come close enough to Jupiter and become perturbed, they can either be collected by Jupiter and they can, orbit Jupiter and eventually fall into Jupiter. They can be ejected again, become one of the Trojans or Greeks. They can be ejected again, go back to the main belt, or they can be caught by Jupiter, ejected, and sent to the inner solar system toward the sun, where they either burn up in the sun or they become a near-Earth object, or a combination of both. They become a near-Earth asteroid, and then eventually they may spin into the sun. So Jupiter's role in that is very strong. That's fundamentally what causes a lot of that to occur. The changes in asteroids, and they aren't very, even though they've been there for a very long time, the asteroid belt is not exactly static. Things are being thrown out of it or brought into it on a regular basis. So to learn about some of these asteroids, 2 science missions that have been or that are contemporary, I guess, let's say, is OSIRIS-REx. That and Psyche. OSIRIS-REx is notable because it went to the asteroid Bennu. It was launched in 2026. It took 2 years to get there. Rendezvous did 2-year science mission. And that is, I guess it was just after the pandemic when it collected the sample from Bennu, and it is returning to Earth, and those samples will be here in just a few short months. Expected to return to the Utah, or not return, but be delivered to the Utah desert on the 24th of September. Psyche is, now Bennu is a near-Earth asteroid, and Psyche is a main body asteroid. Oh, excuse me, I see there is a typo in the line there. So the Psyche orbiter is going to be the first visit to a metallic asteroid. And it is expected to launch this year. There were some delays and some issues with the program, but it's expected to launch in October and should rendezvous with Psyche in 2029 and conduct, it's just an orbiter, so it's just going to conduct various science missions right there. It doesn't return anything here. We probably have to chip off some of the metal with some, pickaxe or something. I don't know. So all of these asteroids that we've been talking about, they're out there, and the ones that everybody is concerned with are, of course, the near-Earth objects. And so I'll just mention briefly this whole thing: near-Earth objects and asteroids. And near-Earth objects includes comets, and I'll talk briefly about comets at the end, but fundamentally, most of the stuff that we're looking at are asteroids. And even though they're almost always referred to as near-Earth objects, they're actually the near-Earth asteroids. So these objects are orbiting the sun, and they're in a proximity to the Earth. The actual definition of the near-Earth object means that its orbit brings it within 1.3 astronomical units. Of course, an astronomical unit is the average, well, it's a specific distance, but it's about the average distance from the Earth to the sun. And so if an object, a comet or asteroid, orbits in a way that it comes within 1.3 astronomical units of the sun, then it's classified as a near-Earth object because it potentially comes close to the Earth, even though 0.3 astronomical units is a good distance away. It could come no closer than the outside of Earth's orbit, but it's still possibly, it's still near. It doesn't necessarily represent a hazard. Now, the potentially hazardous ones are the ones that come within 0.05 astronomical units, or about 4.7 million miles of Earth's orbit. And that's a big area, it's a small area astronomically, but it's a big area in practice. The reason for that is because we don't really know where everything is in space. I mean, we think we do, we say we do, but we have a good idea about it, but its accuracy is not really good. And so when you're plotting the orbits of asteroids, there is an uncertainty ellipse because we don't have GPS for the satellite, for the asteroid, and we don't have any way to verify the precision of its location. So this elliptical area, which is uncertainty about where exactly the asteroid will come, is the measurement of whether something presents a danger to the Earth. If that area of uncertainty touches the Earth's orbit, then it could potentially collide with the Earth, and then you will need more observations to refine the orbit and reduce the uncertainty area to a point that you can be sure that the asteroid will not hit the Earth, or the uncertainty could be reduced in a way that makes it more certain that it's going to hit the Earth. And the other condition for a potentially hazardous asteroid is it has to be 140 meters across or bigger. This size is actually a odd, actually comes from the idea of both the amount of damage that would be caused by the asteroid, but also an asteroid that has a certain brightness, and that brightness was generally equated to be a surrogate for 140 meters in size. It turns out that has not always borne out to be true, and the optical observations of satellites are not especially accurate in terms of their size, which I think we will see in a moment. And then just dotted on here is the orbit of Bennu as well. There are 4 classes of near-Earth asteroids, and these are essentially, I guess I should say there's 25,000. They're thought to be about 25,000. I can explain more about why they think that later, but that's the approximate number. So out of 1.3 million, it's not very many that are here near the Earth. And the number of potentially hazardous is even less. These 4 classes all just have to do with the orbit of the asteroid in relationship to the Earth. So asteroids that's orbit is essentially entirely outside the Earth's orbit are Amors, and they're named after asteroid 1221, which got the name Amor. The Apollos are asteroids that cross, but the semi-major axis is larger than the Earth. So basically their orbit is bigger than the Earth's orbit, but they still cross through the Earth's orbit and cause potential opportunity for collision. The Attens are very similar, except their orbits are essentially smaller than the Earth's orbit, but they still cross. And the Atreas are all inside the Earth's orbit, but they still come close to the orbit, so they could also be potentially hazardous. Okay. Okay, hopefully this is going to work. So this is a little demo I have here for you. I have to share the other screen. Do you see?
Right now, we don't see it. Oh, there it is.
You see it? All right, excellent. So this is NASA's 3D visualization of the solar system. And here you can see every known near Earth object in blue. The named asteroids are in white. You can see the orbits of Earth, Venus, and Mars. And oh look, I still screwed this up. It's yesterday, about the right time, but yesterday. So you can visualize these in 3D, and you can zoom in here and then get, there we go. You see that, and then you can speed this up because, you know, on an astronomical scale, to get solar systems very large, and nothing looks like it's happening, but actually things are happening. You can accelerate this and watch all these asteroids fly around. It's actually quite interesting. A couple months ago, I did a little experiment with the asteroid that is supposed to come by the Earth in 2029. There'll be an asteroid, the name is escaping me right now, but the asteroid will come so close to the Earth that it will be visible with the naked eye. But I believe that is not expected to collide with us. So let's go back to there we go, back where we were, right? Okay, so how do we defend Earth from all of these asteroids? Okay, so this is the part where, in case you're tired of me talking, I'm going to talk more. First, you have to detect the asteroids, and this is basically so there are organized surveys, which you'll see in a second, and there are also amateur observers. There are all manner of telescopes pointed at the sky looking for asteroids. Sometimes asteroids are observed while looking for other things. So they essentially are photobombing, much like the Starlink satellites, except further away. They're in an image of something else, and you say, oh, this is an asteroid. Well, all of that information gets sent to the Minor Planet Center, which is an organization of the International Astronomical Union in Cambridge, Massachusetts. And that is the global clearinghouse for all asteroid orbital data and identification. They assign the identification to asteroids as they're detected and, you know, identified as unique asteroids. Then, and so that is essentially where the tracking is done. And so the detection takes in the past, it's all taken 3 observations to at least to try to determine the orbit of an asteroid. Subsequent observations are very important to reduce that uncertainty ellipse so that you have a good idea of where the orbit actually is. So once you've detected it, you can get more people to look at it, and the Minor Planet Center puts out notices and says, these objects have been observed and we'd like to get more observations. They collect more observations, they refine the orbits. Characterization means that you would like to know what an asteroid is made of, not just how big it is, what it's made of, not just what its orbit is, because those things are important to know if an asteroid is potentially going to hit the Earth. If you want to mitigate the threat, you would need to know what the asteroid is made of. If you can't mitigate it and it's going to hit, you'd like to have a good idea of what the effects will be. All of that requires knowing something about the composition of the asteroid and its size. The risk assessment is essentially performed in 2 organizations. One is the Center for Near Earth Objects in a program called Asteroid Watch at the JPL in California, and the other is performed near Rome by the European Space Agency. They both maintain separate asteroid risk lists. And so if an asteroid, if its ellipse of uncertainty is going to touch the Earth, then they are put on a risk list. You can go and look at, I don't think there are any, there is an asteroid which is coming in the future, which is potentially on the risk list. I don't think there are any others on it right now. There are some that they watch closely, but they don't think it's an issue, but there's nothing really risky going on right now. If something were coming toward the Earth, there are 2 things you can do. You can try to mitigate it, or you can just prepare for it. And that depends on what the potential ramifications are, I guess. So if it's small asteroid, you're probably not going to try to send a giant rocket mission to go out and deflect an asteroid that is smaller than 60, 75 meters, 100 meters. Because that will be a lot of effort, and those are likely to blow up in the atmosphere. The question is, again, what's it made of? If it's a solid metal asteroid, then it can cause much more damage at a smaller size than the average dust ball. So in addition to the mitigation approaches, which we're not going to talk in depth about, but I will answer questions about. There is simulation and exercises that are done. The U.S. government conducts an exercise which is very creatively called the tabletop exercise. There have been 4 of them so far, and it is an interagency, not just government, but it's government and all the involved players from the science community, Minor Planet Center, et cetera. And they have conducted these exercises most recently. I think it was in February of 2020, February of this year, I believe. It was February of last year, 2022, I believe. And these exercises, they give the government a chance to go through the process, narrowing down where the asteroid they think it's going to hit. What is there anything they can do about it? And they explore the options and help the decision makers think through this sort of thing. Simulation, of course, helps you estimate the effect, the results of an impact or results of a mission to mitigate. I'm sorry, that is an error. So this is the discovery statistics for the so-called near-Earth objects. There are about 32,000 that are currently known, and a little more than 10,000 of them are in the potentially hazardous category. As you can see, that really started to take off in the mid 2000s, and as our detection method, as our maturity in detecting asteroids goes up, they're able to find more and more of the smallest asteroids, but the increase in the 140 meter and larger size has somewhat slowed down. I mean, I guess it's sort of been steady. It's not really slowing down, but to get to the point where there are thought to be about 25,000 of those. To get to that point, NASA thinks that it will take more than 30 years from now, or at least more than 30 years from 2 years ago, to find all of them, to reach 90% in that size class with the current detection technologies. So that indicates we need some new technologies. So to what goes into that chart briefly are all these survey programs. These are the current survey programs that are underway that are related to NASA. So there are surveys that are done that are not part of or connected directly to NASA. Europe is doing some. They're working on a new telescope that will be able to detect the asteroids from the ground. And there are other. China is also doing some work. China feeds some information into the Minor Planet Center, but the bulk of the heavy lifting in recent time has been done by these 2 surveys in the center: the Catalina Sky Survey that is run out of the University of Arizona, and the Pan-STARRS telescope. Actually, there are 2 of them now, but anyway, the Pan-STARRS telescopes in Hawaii, the University of Hawaii. Catalina has been doing has discovered more near-Earth objects in the 140 meter size range than any other survey. But Pan-STARRS is now routinely discovering more every year than anyone else. At the top is the NEOWISE infrared space telescope, which I will talk about in just a minute. And here we are. So this telescope is the only space asset that is looking for near-Earth objects. It was launched in 2029, and its original mission was simply to do an infrared survey of the entire inner solar system. It had some technical difficulties. It it nominally completed its original mission, and then basically all the coolant leaked out of its primary IR sensor, so they put it into hibernation. It was put back into service because they decided that two of its remaining sensors would be very useful to look for asteroids. And so they started doing that in December 2013. 6 days later, they discovered a unknown, potentially hazardous asteroid. So the significance of this is that NEOWISE has really helped inform future infrared, future space telescopes looking for hazardous asteroids. They found that a lot of these asteroids are darker than they thought they were. As many as a third of them are really dark and really hard to see. So using an infrared telescope is the ideal thing, because it can still see these things, because even if they don't reflect light, because it's the change in temperature that it's detecting. They found that the infrared estimates of size are generally twice as accurate as you can do from an optical telescope. And then, but the unfortunate thing is that this telescope is very close to the end of its life. It's really been extended an excessive amount, so it may be out of service by the end of this year. Another forthcoming program that is very useful for near-Earth object surveys is the Rubin Observatory, formerly and also known as the Large Synoptic Survey Telescope. So this telescope has been under construction for years. Like everything, COVID delays. It may begin operation this year. There's a whole program of tuning and bringing the telescope on for science after it does its initial I guess trial runs and testing. But its mission is a 10-year survey of the entire southern sky. It's able to scan the entire sky every 3 to 4 nights. So it will be able to detect asteroids just incidentally to performing its main missions, which are to explore the Milky Way and investigate dark energy and dark matter. So a lot of people have said that this would make NEO Surveyor unnecessary, because this is going to meet the goals of finding all the asteroids. That seems unlikely because of the darkness issue, and also because this is not dedicated. The National Academies had a report. One of their options was to create a telescope very much like the Rubin telescope and dedicate it to near-Earth object surveys. Problem with that is that it could only see the southern sky, so you can't see all of the sky from anywhere on Earth. So that doesn't work so well. And then the best estimates are that after 10 years, although it will find a lot of asteroids, it can't get any closer than 65% of the goal for 140 meter asteroids. So enter the NEO Surveyor, which no doubt you have heard about many times, and NEO Surveyor is hopefully on track. I say hopefully because the debt ceiling agreement means that it will probably not get funded correctly yet again. So for a 3rd year in a row. So this is going to be very difficult and challenging for the program. Its cost had already ballooned because of the delays implemented in the past 2 fiscal years. But let's talk about the good things. So the Webb telescope, JWST, orbits in around the L2 point, which is shown in this diagram with the orange ellipse. And NEO Surveyor is going to orbit around L1 because that provides a better view of the Earth's of the area, the Earth's orbit ahead of the Earth, where it can also look behind, but it can't look at both at the same time. Anyway, so looking ahead, sees a wide view. It has a wide view of the Earth's orbit, and it can also look very close to the sun. So asteroids that are orbit that might orbit and come in very close to the sun and then come back out, it can see. Now, there have been some advances with some telescopes looking toward the sun right after twilight, and there have been some very impressive near-Earth object discoveries. But generally, you can't look this way at all with a telescope, because when you're looking this way, it's daylight, and so that does not work. But for a neosurveyor, it doesn't care that it's daylight, because it's really looking into space. So this telescope has been in work. Well, the idea has been around since the late aughts, I guess, 20 aughts, and it's been optimized and designed for this mission. And it is expected that in 5 years, it will reach that 65% metric of the 140-meter hazardous asteroids, and that it will reach 90% or perhaps exceed that within 10 years. So with a little bit of luck, this will still launch by no later than 2028, and we can start that 5-year clock. And 10-year clock for that matter. I just wanted to mention DART because DART was the first, real test of doing something to mitigate the asteroid threat. It's fabulously successful. It flew a long way. It hit its target, and they reduced the orbital period by 32 minutes, which is pretty significant on a 12-hour orbit. So this is great, and this is a big success, but the problem is there's no follow-up on the books. There's not really even a plan for a follow-up. The next mission that we should see is probably a rapid characterization mission. So like if you find an asteroid is coming toward the Earth in a year to 2 years, what do? Well, you send a space probe out to investigate the asteroid, so you have a better idea what mitigation strategy would be best for it. Because if it's just a bunch of dust and debris, you may not just want to hit it with a kinetic impactor. You might send the debris around. If it's a giant metal thing and it has a lot of mass, you probably can't generate enough kinetic impact. You may not be able to generate enough kinetic impact to energy to do something. But anyway, very exciting for planetary defense. But now that DART is over, the only planetary defense mission on the books, space mission, is the NEOSurveyor. Oops. So I'll just say this briefly. So what about the comets, right? I talked all about NEOs, and I didn't say anything about the comets. Comets are a real problem because if they hit the Earth, it's really bad, because they're going to impact around 3 times faster than an asteroid, and this is just based on the physics of their orbits, and they just are traveling at much higher speeds. So there are, I gave you the numbers of asteroids. Compare that with there are only 4,500 known comets, and 100 of them, I think the guys just saw something else, said 100, it's closer to 120 near Earth comets. Now, that doesn't really mean anything, because many of these comets, like NEOWISE, will never come back in our lifetimes. I mean, this situation will be very different. Whereas near Earth objects that are near the Earth's orbit, they tend to come back, repeatedly and frequently, much more frequently than hundreds or thousands of years. But if an asteroid, as we saw with the Shoemaker-Levy fragments that hit Jupiter, the impact from a comet, they have even an impact on a planet the size of Jupiter. So should something like that be headed toward the Earth, well, that's bad. That's a bad day to be here. The problem is that the comets arrive very unexpectedly. And we don't have to think back very far to see this. In the midst of the pandemic, the only space-based planetary defense mission just happened to discover an asteroid that no one had expected. and its closest approach to the Earth was just 188 days later. So if you don't detect an asteroid until it's already on its way, it's probably too late to do anything about it, because the velocity is high, and comets tend to be, I mean, they're pretty good sized things, because otherwise they would have they would tend to have evaporated during their close approaches to the sun over time. So the things that are out there, the comets that are out there are large, and they do present a very real challenge, but it is fortunately a very, very small and improbable situation. So I would be happy to talk to you about our accomplishments, in planetary defense and policy. The bottom line is that we've done about all we can to try to get NeoSurveyor back on track. We got pretty good support from the Congress last year, but it still put NeoSurveyor behind the power curve. The Chips and Science Act provided some language that made the intent of Congress more explicit to NASA, so this year NASA isn't taking any money out of NeoSurveyor. In fact, they asked for the whole amount that we'd hoped that they were going to request, which was $210 million. But this year Congress decided that they would probably rather cause problems with the budget. So we don't know what's going to happen with that. And but the good news is that key science committees and in Congress are very interested in NeoSurveyor. So we'll see what happens. Oops, I'm sorry. This is what we're supposed to say. So are you convinced there's a danger? I hope so. And what should you do? Well, you should support NSS. Because we're trying very hard to get this asteroid telescope off the ground. And you can tell your representatives and senators that you support NeoSurveyor and planetary defense. And finally, you can spread the word and tell others. Don't tell people they should be worried about asteroids falling on their head. It's not like that. But if you don't plan for the future, then what are you doing? You're planning with failure to plan is planning to fail, right? So, okay, well, that's it. So finally, I'd be happy to take any questions.
Okay, great, Jonathan. Why don't you stop sharing?
Yeah, I'm working on it. I can't see my cursor.
Should be a.
I can't. I'm working on it.
You got it. There you go. Perfect. Well, thank you
Hallelujah.
so much. That was really fascinating. Let's open it up to some questions. I've got a few again that were submitted, and then we can see if we get any that are asked from the audience. But a quick question that was put in, can you explain the difference between planetary defense and planetary protection?
Sure, absolutely. Yeah, very, very planetary defense is about protecting the Earth from collision with a hazardous object. Planetary protection is about protecting the Earth or other planets from contamination from another planet. So specifically, there is an effort as when the samples from Bennu are returned, there is a plan to handle them carefully to minimize the chance of contamination of something from Bennu. Turns out that it's very unlikely. That the general thing is it's not considered a likely threat that there would be something, some sort of organism on an asteroid. But this is a concern more for the Mars sample return mission. There's a whole planetary protection regime that is intended to protect Earth from anything that's on those rocks. Planetary protection is also talked about from the standpoint of if you want to go to Mars and look for life, You want to make sure that you didn't bring the life with you. So you don't want to contaminate the environment that you go to, and then you analyze with something that you microbes or organic materials or whatever that you bring with you.
Very good, thanks. I know some people had that question. You answered already about how many asteroids have been identified. But would you say right now, are we very good at finding and tracking these near-Earth objects, or are we just scraping the surface?
Well, that's a pretty subjective thing. I mean, I think we've gotten pretty good at it. I think right now it's just a matter of, do you think that 30 years is a reasonable amount of time, to more than 30 years, to locate these hazardous objects larger than 140 meters? And the challenge is that, you put a number like 140 meters, which again is tied to basically the reflectivity of an asteroid. That's sort of the original, and also a function. Well, how bright an object and how big would an object have to be a danger? Well, 140 meters would be dangerous, but the problem is there's a large range from 140 meters to 600 meters to 900 meters, and the previous goal of finding all the asteroids larger than a kilometer, that's generally accepted to have been met. There's 850 some of those, so it's not that many, but they're very dangerous. I mean, if something like that were to hit the Earth, it would essentially, it would end our way of life. We would not be having a civilization in the way that we have it today. The difference between that and a 600-meter asteroid, it's not always that clear. 800-meter, you still do incredible amount of damage, and the secondary effects of some of these asteroids, the larger ones, there's some thought that asteroid impacts have actually set off in the past. Really, really large asteroids have set off extra volcanic activity, and all this has sort of contributed to climatic effects, which are either warming the atmosphere more or they're cooling it down, like a nuclear winter scenario. So I think the problem is that we probably don't want. One of the things is that the asteroids are changing. They're not always the same. I mean, so they're not changing from today to tomorrow, but asteroids are getting kicked out of the main belt by Jupiter, periodically on an astronomical scale. I mean, so it's just all sort of a matter of probability and how much risk you want to take. There is good science to be done by studying asteroids, for sure, though. And that's one of the disappointing things that we heard from NASA a few years ago, was that this is not science. And that's just chasing the Webb telescope, which is really, is very, very impressive and very expensive. But, there's other science as well that needs to be done. And this also happens to help us keep humanity safe from, being extinct.
A pretty important thing, right? Question is, how much is NASA currently spending on planetary defense? Doesn't sound like a lot.
Oh, that's a good question. Yeah, so the majority of funding for planetary defense was for DART over the past few years. As DART, in the final year of DART, Neo Surveyor got money, but then they didn't spend the money. It's a long story. So the planetary defense budget is on the order of $45 million a year. So very small by NASA by NASA program standards, and that funds the Planetary Defense Office. It funds, I think they fund some of the Minor Planet Center. They fund some of these asteroid surveys in Hawaii and at Catalina Sky Survey. And there's some other things that I'm not remembering, but it's not a very big. It's not a lot. There's other sources of money that fund these things too. So it's not just NASA doing that. Europeans are funding it. But the largest bulk was DART. And I believe DART was in its last year was on the order of don't quote me, $250 million. NEO Surveyor was a request this year for $210 million, which was a ramp up because of previous years where they didn't get the money that was supposed to be there. But NEO Surveyor will probably be a little more than $200 million a year until it's launched. And then, the upkeep of these is very small. It's usually not even carried as a separate program. It's just part of planetary science budget.
Right. You mentioned the DART program, and I mean the DART spacecraft I think was about the size of a big refrigerator or something like that, and was able to knock this asteroid off its trajectory. But do we actually have any true method to protect ourselves right now? That was a test in a way, and that it showed it could work.
It's the first practical, the first demonstration that this theory is plausible, and it's probably the best. It's the most direct method that you can do easily, and so the main challenge with DART is, again, I was talking about uncertainty and so forth, about where an asteroid is, and that DART, I don't remember how far it had to go. It went a very long way, and it had to be controlled itself. So, you could think of DART like a missile, because it had a seeker on the front that determined where the asteroid that it needed to hit was, and it updated its steering, its guidance, so that it could be at the right place at the right time. And all these things are moving. Dimorphos is moving, and small guys moving around there, and meanwhile DART is everything is moving on an elliptical orbit, and so they all have to get to the right place at the right time. So demonstrating that you could do that was really, I think, an important step. The other ideas, which I could have done a whole talk about the different methods, and maybe that's what people would like to hear next time. But gravity tractor, these things, fundamentally, they're all science and physics. And so you have a reasonable expectation that they would work. The problem is execution. So if you have a really long time, you can go out and do a gravity tractor. So you basically just orbit the asteroid in a certain way that causes it to slowly change its course. There's an idea about using little lasers to heat up one side of the asteroid. Asteroids are actually fascinating. So you think that they have a very peculiar spins, because their orbits are modified by the one side of the asteroid heating from the sun. And so since some asteroids, well, there's a variety of reasons, but actually the thermal radiation of the heat off of the asteroid ends up adjusting its orbit. And if there's ice involved, and anything like in a comet, when the ice is gassing away from the heat from the sun, if there's ice crystals in the asteroid, the same effect can occur. And there's this amazing physics involved with why are asteroids moving in the way that they are. So hitting them is quite a challenge, I think. This asteroid was a pretty good sized thing. We probably wouldn't bother to hit something smaller than that, I think. But as the asteroid size goes up, then the kinetic thing gets much more difficult, because the main thing DART had going for it was a very high speed, and so E = mc squared. So more mass is good, but you got to lift that off on a rocket and propel it at a really high rate, and then steer it, not exactly steer, but get the guidance so that it's in the right place at the right time.
Right. Before we go to a couple questions, I know we're at about 10:15 right now. If it's okay with you, we can go a little bit longer, get a few more questions.
Sure. Yeah, I talked so long. I guess I might as well.
Yep. There were a couple questions that talked about using nukes to do this, like the old movies like
Sure.
Armageddon, Deep Impact. Is that a viable approach?
Well, yeah. I mean, it's sort of the last resort. Uh, because if an object is big enough and you need to move it a certain amount, that these are the biggest guns that humanity has. So that's sort of your option. The physics of it is somewhat challenging. I've read a couple different things, which I mean, some some suggest that this is not. It's not really straightforward because you're not going to blow it up. You just need to deflect it, and then deflecting it is somewhat uncertain because you don't know what the asteroid is made of. So if the asteroid doesn't have enough form to enough structure to remain together, I mean, it could essentially be hit by this energy and just sort of break apart into a bunch of parts. And, some of them will go sprawling away, but maybe not all of them. So smarter people than I have put a lot of thought into that, but it's really the nuclear weapon thing is really the Hail Mary. There have been thoughts about, there's actually thoughts about landing a nuclear weapon on the side of the asteroid before you detonate it. That just presents even more problems than just trying to go near it and setting it off. And so almost any case when you would really do something to deflect an asteroid, whether it's a kinetic impact or a nuclear weapon, you're going to send a number of them because you can't afford that one fail. And, instead of putting all your eggs in one basket, it'd be better to send, 6 small darts than one big dart. And the same goes for nuclear weapons. If you have enough time, you might even see that the effect was what you wanted, but it's uncertain.
Right.
But if you want to be entertained, well, I shouldn't say that entertained, but I find it entertaining. If you go to the Department of Energy website, they have a wonderful little series of videos that maybe do a better job than I did about telling you about planetary defense. And the reason is because at the end they say, well, if you really had to do something, that you'd have to use nuclear weapons, and then that's who would own the nukes for the civilian
Right.
purposes. Well, they have a big role in securing the national nuclear stockpile.
Very
I'll
good.
just answer Dave Dressler's question I see about the coronal mass ejection. The answer, it's funny you bring that up because that somebody wanted that to be included in planetary defense, which is an interesting idea. It is a danger to the planet, a danger to at least human civilization, but it is not part of planetary defense. Everyone understands planetary defense to be about protecting, stopping, about monitoring and stopping things from impacting the Earth and causing damage.
Right. Okay, you got that one question. Joe's question there that connects to NSS about how can NSS increase U.S. political leadership interest so we can get increased funding for astronomical object detection and hazard protection?
I wish I knew.
Yeah.
There's some interest, but we
Can you talk a little bit about what NSS is currently doing in this area?
Well, our main effort is to ensure that NeoSurveyor gets the funding that it needs, and that's right now it's $210 million for this fiscal year, and that's what the administration requested. But the real problem is that the Congress it came to an agreement on the spending cap, what's the word, the debt ceiling, and that is very likely. So this is what you can do: is you can contact your representatives and your senators and tell them how disappointed you are, because that is probably going to impact NASA disproportionately. We hear that nothing is known at this point, but we hear that the budget targets that the committees will have for NASA and these and related areas, not just on that committee, are likely to be less than last year. So the agreement in principle, the agreement says that funding levels will be at last year's level plus some inflation, some amount for inflation, but that's total government spending. And it appears that NASA is going to be among, and other agencies are going to be among agencies that will be getting less money.
Right.
A lot less, probably. I mean, some will be really, really a lot, but yeah, I mean, but this is not anything that I've seen in writings. It's just what we're hearing. So that's really the problem. I mean, this whole disruption of the government means that the agencies like NASA get disrupted, and you want to shut down the government that has problems. You don't want to spend money that you authorized last year. I don't know how to respond to that. But the result was it's not going to be good for NASA, and this is also going to be a problem for programs for the moon program. I mean, this is going to set back all of the things that looked really good a year or two ago. Well, they looked good last year. Maybe not. They didn't look great 2 years ago. It's going to be a problem.
Let me tie in a couple questions that were submitted about international cooperation, the role of the UN. You mentioned that right now most of these efforts are NASA, the European Space Agency is doing a little bit. You said China's looking at, but is it the scientists are talking to each other, but is there an effort on a governmental basis to address planetary defense?
I'm sorry, can you say that again? What, just summarize the...
Oh, yeah. Well, there were a number of questions about international cooperation related to planetary defense.
Right.
And
right.
so just asking, well, clearly in your description, scientists are talking to each other, but are governments talking to each other about planetary defense?
Yeah. So NASA and ESA coordinate together. They basically, so I mean, any way you can think about that is it's like a double check, So Europe has their own risk list they assess, and JPL does their risk list and they assess, and so that's they talk together. The other thing that occurs internationally is the UN has two organizations. One is called the International Asteroid Warning Network, and the other is called the Special Mission Planning Group or something. And so fundamentally, the Asteroid Warning Network is organized under the Committee on Peaceful Uses of Outer Space to bring together governments to facilitate communication about a threat to Earth. So you could get information out. You get information about where an asteroid might hit. And this is becoming more interesting because recently we've detected asteroids and plotted where they were going to impact. Well, they didn't impact; they blew up in the air. Most recently was this asteroid that blew up somewhere near Toronto. It blew up over one of the Great Lakes, but was seen in Toronto. It was a big deal, and that was, I think, the second time that NASA had determined. There was a warning that an asteroid was coming, and they knew the approximate area it was going to enter, and blew up. I see somebody says they heard that. Yeah, it was quite impressive. Yeah. The interesting thing is some of these meteors, and this happens even when there are meteor showers. Some of the debris can be seen on Doppler radar, and so if you look for, I don't have the link available, but if you look around, you might find where NASA has a page that talks about this, and they show Doppler radar images in the Great Lakes area, and they're all these blocky things, which is basically the Doppler shift, or the Doppler reflections from the debris of the asteroid that blew up, or well, technically it's a meteor when it blew up, but did I answer?
Very good.
Okay.
Yep. Let me get just a few more in, because I know we're approaching the 10:30 hour on Eastern time. Ryan asks, could a tourist mission fix the near-Earth object satellite? That might be a tough one, right?
Could a tourist mission fix maybe the NEOWISE?
Probably that's the one, yes.
I don't think anybody can fix it, because it's basically, I mean, it was not designed to work this long. It's not really, it's not optimal for the mission. NEOWISE has a very, very thin field of view. It basically has a slice of the sky, and it's got a large vertical, just for argument's sake, a large vertical thing, and it's just sweeping along, scanning the sky, and so it sees what's in that vertical area. It doesn't, whereas like a survey telescope or surveyor will have a wide field of view, and it'll be able to see a lot of things. You can't see everything, but seeing a wide set of things. I mean, it also sort of lacks the precision to see some smaller things. So I'm not sure that it would be worth.
It wouldn't be worth it, is what it sounds like.
Yeah, I think it'd be better. I think your effort would be better spent trying to save Hubble.
Right. A couple more that were submitted, and then I'll have one final question for you. What is the, this is from Jeffrey, what is the current status of the B612 idea of creating a protocol in advance for dealing with asteroids that can't be deflected to miss Earth, but which can be nudged to impact a different place on Earth?
Oh, well, that's interesting question. So
yeah,
I once saw a thing where I said, if somebody says, well, that's an interesting question, it means they don't want to answer that question.
okay.
I'm not sure that I want to. So first of all, I'm not intimately familiar with the B612's protocol for this. I will say, at the risk of being, at the risk of actually somebody from B612 being angry about this, I will mention that Carl Sagan wrote about this idea that if you could deflect an asteroid away from somewhere, you could deflect an asteroid onto somewhere. And so he wrote an opinion piece suggesting, in fact, he wrote two things that suggested that he thought this was some danger that humanity should not be, this is like the follow-on to nuclear weapons. I don't really put any stock in it, and I'm told that he gave up that view later in life, but you can still read this stuff. It's kind of interesting.
Because anywhere it would land would have an enormous impact.
Well, right. It all depends on the size, right? So that's the first problem. Is that this, depends. It has to be the right asteroid, and it has to be. You have to be able to put it where you wanted it. I mean, if China wanted to hit Washington, you can't just make it. I can't make the asteroid change its direction. You can just. It's a little bit over here, it's a little bit over there. Either it misses the Earth, maybe it doesn't hit Washington, it hits Bermuda. I don't know, but it's along an arc, and it's very difficult. I think that this is well, I think it's a red herring. It's possible, and certainly I think the challenge for international cooperation is working. All right, so I should mention this. So this is the problem, is that if you're going to deflect an asteroid, now you're going to have to talk to other nations, because as somebody asked a question about, is it legal to use nuclear weapons to do this stuff? And the short answer is it's not able to, the short answer is that you could do it, because that would be like saving the world, I guess. But there would definitely be people and countries that would be opposed to this and say this violates the Outer Space Treaty. The Outer Space Treaty prohibits the stationing of nuclear weapons. I don't believe it actually prohibits detonating nuclear explosions.
And
this is generally thought that this would all be coordinated through the UN if this were something that you would need to do, and everybody would just sort of go, okay, well, what else would we do, right? There isn't another option.
I'm just reminded about that, the joke that the tour guides at Meteor Crater always say. There's always some tourist there who makes a comment that not realizing how long ago the meteor struck, it says, oh, it's a good thing it missed the freeway. Right?
Yeah, right.
So they just didn't realize. I see Dale has a comment in there about the asteroids as a poor space-to-space weapons. Let me get yeah, Dale's he's been discussing this topic with Pete Garrettson. A lot of detail. Asteroids probably make poor space-to-space weapons due to gravity effects. They make better space-to-ground weapons. Okay.
So I mean, I think there's better, the effort to do that is, I'm not sure it's worth the return. I mean, we can't even get,
right.
Can't lift the material to make space solar stuff into orbit. I mean, are we really going to be sending rockets to hypersonic? It seems like there's a lot easier ways to,
right,
have weapons that have much less risk and downside than that.
Well, let me get 2 more questions in, and then we'll call it a night because we're way over. But there was one in there about the from RA about asteroid mining.
Well, so the way that it does play in is this idea of, if you wanted to mine an asteroid, what you'd like to do is put it into an orbit where it was easily accessible from Earth. And so you might want to divert an asteroid into an orbit, and that's basically a similar technology to what you would, I mean, potentially one of the same technologies is how you would nudge it into the right orbit, probably maybe gravity tractor. I mean, I don't know, whatever. But that's probably the main thing. I don't think there's any, generally something that's coming toward the Earth that is considered, I mean, so first of all, the catalog of known asteroids and the science that is that characterizes what they are like, that might be useful for somebody that wanted to go out and mine an asteroid, because it gives you some information to start with, right? Because they're not going out and discovering asteroids. They're looking at asteroids that are known, trying to find out as much as they can, and then just, then go out and see if they can get the resources they think are there out of it. So I don't think there's, you're not going to mine. I don't see any synergy between the threats that are coming and mining them. I guess if it were far enough away, you could mine away the whole asteroid until there was nothing left, and it's so small.
Right. One last question before we close out then, and it's just related to the policy committee. Can you just explain a little bit about what the NSS policy committee does?
Sure. So the policy committee is chartered in the bylaws to essentially manage our positions regarding legislation and action from the government or governments, U.S. governments, U.S. State and state local governments, which primarily would be state and local, would be around spaceports and space launch facilities, although certainly the FAA is a big factor there. So we develop positions on that, on legislation. We develop the positions that are advocated for in March Storm through the Alliance for Space Development. We engage with Congress to help educate them on the things that we think are important. And what else do we do? We work with the International Committee to some degree to for our policies and our views to be presented in conjunction with what their thoughts are at the UN.
Great. I know we talked a little bit about maybe coming back later in the year and having a more detailed discussion about the policy committee. So hopefully we can work that out.
Yeah, sure.
So great. Well, thank you so much, Jonathan. That was great. Very interesting topic. And we really appreciate all the effort you put into putting that together and making the presentation. So really do appreciate it. I would like to give a last word to see if he has a last word for us. Our COO, Dale Scran, is on our call. Dale, did you like to make a final comment before we close out?
Yeah, sure. I just think we're really lucky to have John as our policy chair. It was a great talk. I really enjoyed it. And I learned a lot. I hope that you all learned a lot. And I know that Isaac Arthur was unhappy that we didn't give him enough advance notice to tell his audience about this, because this is the kind of talk that his audience is interested in. But since we're recording it, I think we can fix that problem. So we need to make sure that Isaac directs his audience to watch this video. Anyway,
Sure.
thanks again, John.
Yep.
Yeah, sure. Thank you, Dale.
Yep.
Hey,
Thanks,
I
John.
want to apologize. Somebody asked about how many megatons was the well, they didn't directly
Yes.
Donald Loeb. I should know that, but I don't know it offhand, and I just couldn't find it on the screen. But I will, if you drop your contact information, I'll tell you. All these estimates are very vague.
Yeah, I could also send it out when we send out a copy of the presentation, the copy of the session tonight. We usually send a link out, so we can also include that. Great.
I'll try. I should know that. That's terrible.
Well, very good, everybody. I think with that, we're way over, which is, means we were really having a great conversation. So again, Jonathan, thank you so much. I'd also like to thank my colleagues, Larry Ahern, VP of Membership, and Fred Becker, who always does our tech for this and helps promote these events, for everything they do to support the Space Forums. I thank everybody for attending. I'm going to share my screen one last time as we close out the session tonight. So let me just do that. So everybody, again, thank you so much for attending. We're good to be back on track for our Space Forums. So we'll see you again on July 13th. So look for the announcements. For those of you who are in our time zones, have a great rest of the evening. If you're in tomorrow's time zone, have a great day. And of course, have a great weekend. Stay safe. And we'll see you all on the 13th of July for the next Space Forum. Take care, everyone, and good night.